we'll just bring up the slides. And this is where we were the last day. Okay, this is the last thing we looked at in the tutorial, and it's really a terrible stretch to get to that. Just let me fiddle here for a second. Okay. Now, what the information here is about an instruction, and this is well beyond what it's reasonable to expect you guys to know about. So please don't take fright at this point. But I'm talking about the details of an instruction, and as I say, I realise I'm jumping the gun a bit. But what I'm saying here is that, well, let's just step back a little bit and think about what you do know about the microprocessors and so on. There's that von Neumann architecture, which I'll show you in a moment again. The von Neumann architecture, where you have the CPU, you have memory, you have peripherals, and you have a bus joining them up. Okay. Now that's a slightly more complicated model in ways of the system than you need, and we'll simplify it in a few minutes. But roughly speaking, what you've got is you've got the CPU where everything gets done, and you have memory where everything gets stored. And let's forget about the peripherals. So if you wanted to, you might remember that what we wanted to do is get the average of 10 numbers. If you want to get the average of 10 numbers and they reside in memory, well, clearly then, if you can't do anything in memory other than store information, you have to actually bring it down into the processor. You have to do whatever is necessary down there, including divide, okay, to get the average, and then store the result perhaps back up in memory. So even in that most general way, you roughly know what to do. And if I gave you the instruction set summary now, you'd scrabble around and try and make some sense of it, and you probably would make a fair fist of it. But let's go on a little bit and see, sorry, going the wrong way here by the look of it. Maybe not, hold on. Ah, yes, okay, sorry. That slide shouldn't be there. Okay, so just to refresh your memory, here's the programmer's model again of the computer system. We have the CPU, memory, the peripherals, and initially we're just going to throw most of that detail away, and we're going to end up with this. Okay? This is a simpler version. And the three components in it are all important, right? We have the 68,000 processor microprocessor here itself, and that'll be the CPU in our von Neumann machine. Okay? We'll have memory. Okay? We'll have memory over here, and memory is organized the way it's shown here. Okay? Each location in memory is numbered, starting at 0. And on the 68,000, it goes up to 16,777,215. Okay, and that, for your information, that's 2 to the power 24 minus 1. As we'll see later, we'll talk a bit more about it. And each location holds 1 byte of information. So we would say that the 68,000 is byte addressable. It's byte addressable. Okay, so you have the processor, where everything gets done. We're going to talk a good bit more about that, and I've given you a handout which we'll talk about. You have memory over there where stuff gets stored, and joining them up is the bus. And the bus is bidirectional. Okay, information can go from the processor to memory, and it can come from memory to the processor. And by the way, in our versions of the computer system, these transfers of information on the bus will always be under the control of the computer, of the processor, not of memory. Okay, so that you can think, if you want to sort of try and think of this as if these were humans in a sense, you could think that you're the processor. You're standing, as it were, in the processor, and the processor is the one that gives orders to transfer information into it or to send information away from it. Now, we can then talk about a read on the bus. Okay, so if you're standing here and you're looking for information, you're reading information from memory into the 68,000. If you're sending information for storage out in memory, you're writing it. So you read from or write to memory. They're the verbs that you could imagine using. Now, I should say, and I always forget to say this, anytime we're in virtually any computer that you can think of, whenever you read information, say from a particular location, what you'll be doing is actually reading a copy. It's non-destructive. You'll make a non-destructive read of the information that's there. At least that's how it will look. At the lowest level of the architecture of a dynamic RAM, it actually is destructive. When you read from a cell, the contents of the cell are obliterated in the process of reading it, and it has to be reconstructed. Well, that's okay. But as far as we're concerned at the level of assembly language, you're doing a non-destructive read, a copy from some particular place, whether it's a location in memory or somewhere else. It's a non-destructive read. When you write something, however, if you write a byte into location 6 there, then what will happen is whatever was there before is obliterated as if it never existed. There's no connection between what was there before and what will overwrite it. Okay? So reads and writes. Now, the other thing is the bus. The bus itself imposes a penalty on everything that you do. The bus is slow, like all buses. Sorry, hope nobody's from CLE here. But it's slow. Electrically speaking, what's happening is the 68000's electrical or electronic hardware is trying to impose signals on the wires that make up the bus, which have to propagate through the CPU, through the computer board, and maybe even further afield. They have to propagate through that to get into the memory system, which is going to take a bit of time to recognize them and use them. That's if you're sending information out. If you're taking information in, a similar thing has to happen. So transferring information on the bus is slow, and it also takes up a certain amount of energy. Although we're not going to worry about the energy side of it in this course, nevertheless you need to think about it. So if you can get away with not transferring information across the bus, so much the better. And you say, what? Well, suppose you have a piece of information that you need to do a couple of things on. You could take the information from memory, process it, store the result back in memory, take a copy from memory again, process it again, store it back in memory again, take it back to the processor again, and so on. Okay? And if you're using a primitive compiler, some of the earlier compilers, that's what would happen. Okay? You'd have a lot of transfer to and from memory. What you could do, though, if you think about it, as a good assembly language programmer or a good compiler now, will take the information the first time, and if it's possible, it will keep all the copies locally. Okay, so it'll take the information the first time, perform the first operation on it, and not send it back out to memory. It will perform the second operation on its local copy. It will perform the other operations on its local copy. Yeah, I hate that. I'm going to have to fix that. That's a real PC-ish thing. To interrupt you while you're doing something there. Your system needs to be restarted. Isn't that what it often says? You know, that's the usual answer for that. Okay, and I will get rid of that syndication agent and all that stuff later. Okay, yeah. So what you could imagine then is having a local copy of that piece of information. Now that's fine, and it works if you're thinking of one processor in your system. But in the not too distant future, you'll be working on multi-core processors, right? And it might be the case that you have the original copy up here, and you'll have a local copy which has been altered here, and somebody comes looking for it, another agency comes looking for it. Do they get the local copy, which is the most up-to-date copy, or do they get the copy that's out in memory? So there are issues that you have to deal with through a thing called typically cache coherency, right? But for the moment anyway, we just have to note that using the bus is costly and we should try to avoid it. Okay. Now, okay, let me just go back again. This is the 68000. You can see it's a white box, a yellow box in this case. Now we're looking inside. You want to look inside the 68000 because you need this programmer's model to enable you to figure out what to do. Okay, now think about that, getting the average of the 10 numbers idea. Well, inside the 68000, this is the arrangement that you might be able to see. Let me take you on a quick tour of it. And this comes from the 68000 programmer's manual, and it's not exactly what I would use. But anyway, there are 16 general purpose registers in it. 16, okay? And each register is 32 bits wide. And you'll remember the bit numbering that we were using from bit 0 to bit 31. Okay, 32 bits. So the 16 general purpose registers, there's 8 data registers. They're called data registers, D0 through to D7. So each one of those is capable of holding 32 bits. Okay, and then there are 8, not 7 as it says here. There are actually 8 address registers. Okay, and the 8 address registers are A0 through to A7. Now, this diagram separates A7 from the other address registers for reasons which I'll come to later in a couple of weeks' time. But for the moment, you have 8 data registers and you have 8 address registers. And their general purpose, they're for holding data of some kind. The names that they have, like data register and address register, are a little bit misleading, but I hope you'll see why they're called those in a little while. What they are for is for holding information temporarily. So let's imagine this averages business. You might, for example, say, okay, well, I'm going to take the 10 numbers down from memory, and I'm going to stick them in any registers I can find. Okay, so you might put the first one in D0 and the second one in D1 and so on. And they're for holding things. So they're a place to put something down in the processor. Now remember, these are not memory locations. These are actually in the processor. So access to them is instantaneous. If you want to get something in a data register or an address register, it's instant because you don't have to go across the bus to get it. So if you can hold something in a register, you've got very fast access to it. Instantaneous access. These registers are organized, the data registers are organized so that they can manipulate either 8 bits at a time. Okay, that's what this dotted line here means. In other words, you can treat a data register as if it's only 8 bits wide, or you can treat it as if it's 16 bits wide, or you can treat it as if it's its full 32 bits. Right? So if you have characters, and you've seen characters are 7-bit ASCII code is used for encoding characters. Typically, you'll put 7 bits in an 8-bit byte. So if you're processing characters, typically you'll be using just the byte part of these registers, right? Excuse me. So the data registers then can be treated as if they're 1 byte wide, 1 word wide, or 1 long word wide. And whenever you operate on a register as something less than 32 bits, let's say you operate on it as a byte, whatever you do to that byte, it'll have no effect on the other 24 bits. Okay? So it's as if you just chopped any operations off at this bit number 7 boundary here. Whatever you do to, say, D5 here as a byte will have no effect whatever on the rest of the contents of the register. So whatever contents they had before, they'll retain. So that's an important point to make. Some instructions, as we'll see, allow you to manipulate bits by themselves. And they typically operate on pieces of information, so-called operands, inside data registers. But we'll get to that in due course. Now, if you compare the layout that's shown here for data registers and address registers, you can see that there's a slight difference. And the difference is that with an address register, none of the instructions that the 68000 has implemented allow you to manipulate the byte part of an address register. You can only treat it as either a 16-bit wide yoke or a 32-bit wide item. Okay, so there are some differences between the data registers and the address registers as to what you can use them for. So they're not totally interchangeable. All the data registers are interchangeable with one another. All the address registers, well, A0 to A6 are interchangeable with one another, but they're not interchangeable as between, say, address registers and data registers. So sometimes when you're looking for speed, you're going to have to say, well, will I put this piece of information in an address register or a data register? Have I got room? Have I got a spare register? Will I put it in an address or a data register, depending on what I'm going to be doing with it in the future? Okay, so there are 16 general purpose registers. To begin with, just think of them as just places you can hold things. Now, underneath them, in the hardware of the machine, there's all the hardware necessary to do things like addition, because you can issue an instruction to the 68000 to take the word contents of D4, say, and add it to the word contents of A4. And so underneath, when that instruction is issued, the hardware in the processor takes the bits from these registers, performs the appropriate operations on those bits, and maybe puts a result somewhere, say back in A4 or D4, wherever you specify. Okay, so underneath this surface level, there's the hardware that gives effect to the instructions that we issue. Okay, so you'd imagine bringing information in here, processing it, and then maybe storing it back out into memory later. The other two registers here, these two registers here, are special purpose. They're not general purpose. The first one here is the PC, the program counter, not personal computer or anything like that, or politically correct, but program counter. And the second one here is called the status register. Okay. Now, what are these for? Well, okay. Now, let's see now. Okay. If you think about memory for a moment, memory is numbered, as we've just seen, and as we see a bit more of, I hope, in a couple of minutes. It's numbered. That's fine. Memory contains data, which is fine, and it also contains programs, which is fine as well. The programs are sequences of instructions, okay? And they're encoded in binary and stored in memory. Okay, now in the 68,000, instructions are at least 2 bytes long. They're always an even number of bytes, and they can be from 2 to, I think, maybe 10 bytes long. Okay, it doesn't really matter at this point, but they occupy memory. And therefore it follows that every instruction in a program must have a location in memory, the memory that it occupies. Okay? And so if you imagine a sequence of instructions, they're going to be stored in memory in sequential memory locations. Okay? Now in the von Neumann machine, when you're executing a program, you're executing it instruction by instruction. And let's say you're executing the current instruction. Okay, that's going to be in memory somewhere. Okay? And by default in the von Neumann machine, the next instruction that's going to be executed is the one that follows this instruction sequentially in memory. And that's what this program counter points to. The program counter is run by hardware underneath and is always made point to the next instruction to be executed. Okay? So if you're executing an instruction that starts at location, say 1000, and it's 4 bytes long, the next instruction, which will be in the PC, or sorry, which will be pointed to by the PC, will be at 1004. Okay, and so on. And the von Neumann machine makes this assumption that the next instruction to be executed is always the next sequential instruction in memory, and that's very handy, because otherwise you'd have to have some extra program or extra hardware to work out where the next instruction was to be found and to fetch it. And so it's a feature of the von Neumann machine that as a kind of an optimization, the next instruction is always the next sequential instruction in memory. Okay? Except when you want to change it. So suppose you have a sequence of instructions in memory, and you can imagine them laid out one after another. As memory locations increase, you have the instructions here. And program execution then would go step by step by step by step by step. Suppose you wanted to actually implement a loop, okay, a loop, and you wanted those instructions at the start to be executed again. Well, then what you'd be doing is you'd be saying, I wanted to go this, and I wanted to go back up here. You'd want to change the default way that instructions are fetched. And the way that you would do that by reference to the program counter is change it. So at a particular point, if you said, well, actually I want to branch back to location 500, you would put 500 in the program counter. And that's called a branch or a jump. And we'll see the instructions for that later. So that's what the program counter is. The program counter always points to the next instruction to be executed. Always. Supposed to. Okay. The other register here is also a special purpose register. Oh, and by the way, sorry, the program counter is logically 32 bits wide. Okay. In the 68,000, only the rightmost 24 bits are used. The upper 8 bits are not used in the 68,000 itself. Okay, but logically it's 32 bits wide, and you should treat it as a 32-bit wide object. What else is there worth saying about that just before I go on to the status register? It might be just worth saying that it's clear that the program counter is a number. Any address, any location of anything is itself a number. So, as well as being able to manipulate numbers that correspond to data, suppose you have a matrix of, intensity values in an image, that's clearly data. Those numbers correspond to data. But as well as being able to manipulate data with instructions in the 68,000, because locations are numbers, it should be possible to manipulate locations as well. And indeed it is. It's possible to calculate where a particular thing might be, to use instructions to generate a number which is the location of something you want to get. So you can have this level of indirection. You can actually figure out where something, you can use instructions to figure out where something is to be found. And we'll see that the duality there that an address, a location, is both the location of something and a number in its own right. We'll see that being used later on. Okay, so moving on to the status register then. The status register is a place where the overall condition of the computer is kept. For example, we'll see later on that the computer can be run in two modes of security. One called the user mode and the other called the supervisor mode. That information is stored in the status register, in part of the status register. We'll also see that the 68000 is capable of responding to events that occur in the outside world in what are called interrupts. And we'll see that the priority of the program that's running with respect to the priority of these incoming requests, that priority is stored in here as well. For example, you might have a low priority request coming in from outside saying I want some service, and the 68000 might be running a program at a high priority, and it will basically say I'm not going to bother with that low priority request because this is too important. So you have this priority business. That's stored in the status register. Now the two examples that I've given are long-term status or status status data about the 68000. But from instruction to instruction, certain pieces of information can be posted and stored in the rightmost half of the status register, and that's called the CCR, which stands for the Condition Code Register. The Condition Code Register. So, roughly speaking, this is what goes on. Instructions are being executed and results being generated and possibly being stored in registers and stored in memory. As well as that, and alongside it, typically an instruction will post a kind of a summary in the condition code register. Okay, kind of a very short summary. For example, it'll store a result. It'll indicate whether the result was 0. It'll indicate whether the result was negative, and a few other summary pieces of information like that, which is very useful for controlling the flow of program execution, among other things. Okay, so this is the programmer's model. Okay, you'll be writing a program. You have memory, you have the bus, you have the processor with its registers, you have instructions. That's the world that you have to live in when you're trying to write some code. So let's go back and let's think about our little problem. We have to calculate the average of 10 numbers? Is that right? So clearly we could, and sorry, let me just back up a little bit. And the numbers themselves are stored as words. Isn't that what I said? 2 byte wide items. I think that's what I said. Maybe I should just go back on the old slides here. Yeah. Okay. Write an assembly language program to find the integer average value of 10 unsigned word integers. Of course, I haven't said what an unsigned word integer is, but we'll gloss over that for the moment. The numbers are stored at an array starting at location 2000 in hex. So the result should be stored at 1FFE. So where is 1FFE relative to 2000? Can anybody tell me? Trivial question. It's not 8 bytes, no. Sorry, I heard it over here. 2 bytes. It's 2 bytes. 2 bytes ahead. So you have 1FFE, 1FFF, and then 2000 in hex. Okay, trust me, I know. Okay, so that's what we want to do. So looking at our programmer's model, this one, or